What's up, everybody? Today we're going to be starting a quick little unit on vectors. In this lesson, we're going to focus on objective number 1 here, which is being able to add, subtract, and scalar multiply two vectors, okay? So understand a vector is a directed line segment that has an initial point and a terminal point associated with it. The vectors are always identified by their magnitude, which is just the length of the line segment, and also by the direction, which is represented by an arrowhead pointing towards your terminal point. So here I have pictured vector AB. Point A would be your initial point, okay? And point B would be your terminal point since the arrow is pointing towards it. All right, now as far as notation is concerned, you can represent vectors a few different ways. So one way would be to use the letters that represent initial and terminal points. So notice we have vector AB here with a line segment above, or a ray above AB. So that's one way you could represent it. You could also just use a single letter. In this case, we're using V. And one way would be to just write the arrow over top of the V. Or often textbooks, instead of doing that, they'll write a V in bold. Okay. Now we can't, by hand, write numbers in bold or letters in bold very well. So we're just going to typically use the arrow notation. Okay. Now, a vector with magnitude 0 is known as the 0 vector, and it can be represented with a bold 0 or just 0 with an arrow above it. Understand the 0 vector, it has no direction, meaning the initial point and the terminal point, they're both in the same location. Okay. Two vectors, V and W, they're said to be equal to one another as long as they have the same magnitude and the same direction. Okay. So here I have pictured two vectors that are in fact equal to each other. Notice they're not positioned in the same location. Their initial points are not in the same spot, but they don't have to be in order to be considered equal to each other. Notice both of these vectors are of the same length and they're both pointing in the exact same direction, so they are said to be equal to each other. Okay. All right, now we can represent vectors with what's known as a component form geometrically in a grid. Okay, so vector V has components here of A and B. Now notice this looks a lot like an ordered pair, except instead of parentheses we use these little symbols. Okay, component A is known as the horizontal component of the vector, and then component B would be your vertical component. And these two numbers, A and B, all they do is they tell you how many units horizontally and vertically you need to travel from the initial point of the vector to get to the terminal point of the vector. Okay, so over on the right here we have vector V with components of 6, 4. That just means to get from the initial point to the terminal point, you're going to move 6 units horizontally to the right in the positive direction, and then 4 units vertically in the positive direction to get to your terminal point. Okay? To drive this home, let's pull up this illustration. Hope you see this a little bit better. All right, so here I have vector AB. We're using the notation based on the initial and terminal points. And it has components of 9, -4. So all that just means is to go from point A to point B, you're going to have to travel 9 units horizontally in the to the right, and then 4 units downward, since 4 is negative, to get to point B. And then notice that black arrow there, that represents your vector AB. Okay? All right, so based off of that, let's find components for each of the vectors graphed here. So let's start with vector W. Vector W, to go from the initial point to the terminal, I'm going to have to travel 1 unit right and then 3 up. So the horizontal component is going to be positive 1. The vertical component is going to be positive 3. Okay. For vector v, to go from the initial to the terminal, I'm going to travel 2 units right and then 2 units down to get to that terminal. So the horizontal component will be positive 2, but then the vertical component will be negative 2. Okay. All right, now we often use the rectangular coordinate system to represent our vectors in the plane. When you have a vector whose initial point is at the origin, it's known as a position vector. A position vector is a point or a vector whose initial point is at the origin. So here in the picture, I have 2 vectors that are equal to one another. It's just one's a position vector, the other is not. So the vector traveling from point 1 to point 2, that is not a position vector because its initial point, point 1, is not at the origin. Okay, but vector v is considered a position vector for the original vector from P1 to P2. So notice vector v, its initial point is at the origin. And then notice it has the same horizontal and vertical components as vector traveling from point 1 to point 2. Also notice that the terminal point for vector v is 5, 4. Those numbers match the components of the vector. Okay? All right, so let's find the component form of a position vector v from point 1 to point 2 here. So let's start by drawing out the vector from point 1 to point 2. So point 1 is right here, and then point 2 is right here. Okay, and we're going to draw our arrow pointing from point 1 to point 2. So notice this is, of course, not a position vector since the initial point is not at the origin. Okay, it has a horizontal component of 6 and a vertical component of 1. Okay, so I'm going to say that vector v, the position vector that we're about to create, should have horizontal component of 6, vertical component of 1. And then to graph that position vector, we just have to place our initial point at the origin, move 6 units to the right, and 1 unit up. Here's our position vector. Okay. Now understand, in order to get the components of 6 and 1 here, you don't actually have to graph the original vector from point 1 to point 2. You could just use a little bit of algebra based on the coordinates of point 1 and point 2. Okay, so this 6 can be found by taking the x-coordinate of point 2, and which is 4, and subtracting it by the x-coordinate of point 1, which is negative 2. Okay, and then similarly, the vertical component of 1, it can be found by taking the y-coordinate of point 2 and subtracting it by the y-coordinate of point 1. Okay, so that's how you can algebraically find those components for the position vector without actually drawing everything out. All right, now let's get into the operations between two vectors. So a resultant vector is the vector that's produced by the operation between two or more vectors. So we're going to look at addition, subtraction, and scalar multiplication to lead us to resultant vectors. Okay. You will notice in this example, I already have my two vectors in their position vector form. Okay. Notice both of these vectors, their initial points are at the origin. All right. Vector W has components of 2, 3, and then vector V has components of -1, 3. Okay. All right, so let's say I want to add the two vectors together. I want to do vector V plus vector W. I'm going to do this with what's known as the triangle method, or sometimes it's referred to as a tail to tip method. Okay. And before I actually get to this example, let's give you another illustration. Okay. All right, so let's actually shrink these down a little bit. There we go. All right, so here I have vector U and vector W that I'm trying to add together, okay? Vector U has components of 3, -4. Vector V has components of -5, -4. So the first thing I'm going to do is form these vectors, okay? So here would be vector U, and then here would be vector V. Okay. Now, if I would like to add these two vectors together, let's say I'm doing vector U plus vector V, all I need to do is I draw out vector U, and then I place the terminal point, or I'm sorry, the initial point from vector V at the terminal point for vector U. Okay. So again, I've placed the initial point for vector V at the terminal point for vector U, and then here would be the sum of those two vectors right there. So notice why this is often referred to as the triangle method, because if you draw all three vectors out here, the original two vectors and the resultant vector U plus V, you end up with a triangle. Okay. All right, so let's perform that on our example here. So if I want to do vector V plus vector W, I'm going to first draw out vector V. Okay. Again, it had components of -1, 3. So I place that initial point at the origin. I move 1 unit left, 3 units up. Here's my vector V. From that terminal point of vector V, I now draw out vector W. Okay, so I'm going to move 2 units to the right and 3 units up. Okay, so this was vector V, this was vector W, and my resultant vector, the sum of these two, would be this vector that points from the very first initial point to the final terminal point. So the vector in blue here, that's my resultant vector. Okay, now what are its components? If I go from the initial point of it to its terminal point, I'd have to travel 1 unit horizontally to the right, and then 6 units vertically. So components are +1, +6. Notice how I could algebraically have found those components of 1, 6. You simply just have to add your horizontal components from the two original vectors together. If I add those, it'll give me 1. And then add the vertical components together, it'll give me 6. Okay. Now, let's go in the other direction. Let's say I want to find W plus V. So this time I'll start at the origin, and I'll draw out vector W first. Now, vector W's components were 2, 3. So move 2 to the right and 3 up. So there's your vector W. And then off of that terminal point, draw vector V. Okay, which again was 1 unit to the left and 3 up. So there's vector v. And my resultant vector would be this one. Okay, and what I want you to notice here is that the final vector is the exact same vector as when I added vector v with vector w. Still get 1, 6. So what that tells me is that vector addition is commutative, right? Vector v plus vector w should be the same as vector w plus vector v. Okay? All right, now let's get to subtracting vectors, okay? And I'm using the same 2 vectors that I did in the previous example here. In order to subtract 2 vectors, you first have to have the concept of the negative of a vector, okay? So I'm going to start by finding the negative of vector v. To do that, you simply draw the vector in the opposite direction, okay? So if vector v originally had components of negative 1, 3, the negative of it would be having components of positive 1, negative 3. Okay, and if you were to draw that out starting at the origin, you'd have you'd go 1 to the right and you'd go 3 down. Okay, so notice, isn't that just the same as vector v, just going in the opposite direction, right? Here's the original vector v. You draw it in the same grid. Okay, so just same initial point, heading in the opposite direction. Okay, so to subtract 2 vectors, you're actually going to be adding the negative of the second vector. So if I want to find vector v subtracted by vector w, that would be the same as if I took vector v and added the negative of vector w. Okay, so let's we'll have to start by drawing out vector v first. Okay, so vector v is right here. And then from that terminal point of vector v, I'll now draw out the opposite of vector w, or the negative of vector w. Now vector w, normally you move 2 to the right and 3 up in order to get to its terminal point. So now I have to move 2 to the left and 3 down. So this would be the negative of vector w, and I'm going to say my resultant vector, I'm going to use purple this time. This would be considered v subtracted by w. Okay, so what are the components of it? Well, you have to travel from the initial point to the terminal point 3 units left. So that's negative 3 for the horizontal component. And then you don't have to travel any units vertically, so 0 for the vertical component. Okay. Now notice algebraically how you could have gotten the negative 3 and the 0 just by using the original components of vector v and vector w. So if you took vector v's horizontal component, which is negative 1, and you subtracted it by w's horizontal component of 2, negative 1 minus 2 gives you negative 3. Okay. And similarly, if you just subtracted the vertical component of vector v by the vertical component of vector w, 3 minus 3 gives you 0. Okay, so it should be really easy to do algebraically if you're given the components of the original 2 vectors. Okay. All right, lastly, let's look at scalar multiplication. Okay. Again, same 2 vectors as the previous few examples. So let's say I ask you to find 2 times vector w. So first, let's understand this 2 is known as a scalar. Okay? And all that wants us to do is find the vector with the same direction as vector W, but double the magnitude of vector W. Okay? And I can get its components very easily just by doubling the components from the original vector W. So that would be 4, 6. Okay? So think of it like this. 2W would just mean draw out W twice in a sense. Okay? So here would be 1W. And then from there, if you draw out a second W, so all together, from the very first initial to the very final terminal, this would be considered 2 times vector W. Okay? So now let's kind of put it all together here. Let's say we want to find 2 times vector W subtracted by 2 times vector V subtracted by 2 times vector W. Okay? All we need to do is draw out 2 vector V's. So I'm going to start in red this time. So here would be a single vector V. And then from there, another vector V. So altogether, this represents 2 times vector V. Okay? And then we have to subtract 2 times vector W. So that means we have to draw out W twice, but in the negative or in the opposite direction of the original W. Okay? So that means from this terminal point, I'm going to move 2 units left and 3 units down. So that would be negative W. And then I do it again. 2 units left, 3 units down. That would be another negative W, which means combined, this is negative 2W. And my final resulting vector, I'm going to use purple here, would be from the very first initial point at the origin, pointing here to the terminal point, the very final terminal point. So that would be 2 times vector V minus 2 times vector W. What are its components? You have to travel from the initial to the terminal 6 units to the left, so negative 6 for the horizontal component, and you don't travel vertically at all, so 0 for the vertical component. Okay? Now, think about how you could have found this algebraically. So 2 times vector V would be nothing more than negative 2 comma 6. That's just doubling the original components of vector V. Okay? And then 2 times vector W would be 4 comma 6. All right, so now if you subtract the components from vector 2 vector V by 2 vector W, negative 2 minus 4 would give you negative 6, and then 6 minus 6 would give you 0. Okay? All right, lastly, just want to finish up really quickly with a couple properties associated with vectors that maybe you observe some of these in these examples. So starting with vector addition, we already said was commutative. So vector V plus vector W is the same as vector W plus vector V. But that's also true for the associative property as well. Okay, so that's just saying you can add vectors in any order multiple vectors in any order, and you should always get the same result. When you add a vector with the 0 vector, it remains unchanged. Okay. If you add a vector with the opposite of itself, you'll get the 0 vector. And then lastly, anytime you take a vector and you multiply it by a scalar of 0, that's going to give you the 0 vector. Okay? So just a few properties that result from all these operations.